Hello, I'm Neil Spooner, the chair of the Patient-Centric Sampling Interest Group, and I'd very much like to welcome you to our latest webinar. This month we're featuring Jayden Lee Roberts of the University of Notre in Australia. He's going to be talking to us about microsampling-based metabolic phenotyping, innovations and enhanced techniques for comprehensive lipid and lipoprotein profiling. Welcome, Jayden. I realize it's midnight for you and you've just had your PhD graduation, so congratulations on that. And thank you for staying up late for us. And hopefully everyone will very much enjoy the content you're going to bring us today. Before we get started, I'd just like to thank our partners and sponsors who are listed on this slide. Without their support of the Patient-Centric Sampling Interest Group, we wouldn't be able to deliver these webinars and the other activities that are really making a difference in moving the dial in patient-centric sampling. Reminder that this webinar is being recorded and in a week or so will be available on the Patient-Centric Sampling Interest Group YouTube channel. We very much welcome your questions. Please use the chat function on your browser to submit the questions, and hopefully we'll have time for those at the end. So without any further ado, I'd like to hand over to Jayden. It's all yours.
Thanks, Neil. I appreciate the introduction. And thank you everyone online for joining to come hear a little bit about my research today. I'm hoping to introduce some of my research into the application of microsamples for comprehensive lipid and lipoprotein profiling. And as part of this webinar, I'm hoping to provide some insight into the methodology, practical recommendations, and also patient perceptions for successful translation of microsamples for these purposes. So I'll see if I can move this slide now. Yep, all working good. So I want to begin my presentation with, I suppose, one of the most fundamental aspects of my research, which is its connection to blood collection. So phlebotomy, for many, is just a routine blood draw, but for others, it's a source of fear, anxiety, and even avoidance, whether it's a child resisting a venipuncture, a patient dreading a needle, or a person with difficult veins undergoing multiple attempts. Traditional blood collection can be an unpleasant experience, and beyond the discomfort, venous sampling requires trained personnel, specialized equipment, and oftentimes large volumes of blood, making it impractical for frequent sampling, remote settings, or vulnerable populations. Phlebotomy is an essential part of pathology testing. And to provide a bit of context, at least for Australia, where I'm based and do my research, pathology is an everyday medicine, and around half of GP visits involve a pathology test, with most of these being funded through the Medicare benefit schedule. This scale alone highlights exactly why reducing the friction and burden of traditional phlebotomy could have a big system-wide impact. So the question essentially then becomes, how do we keep the clinical value of pathology but make the sampling step dramatically easier? One approach that's gained a lot of traction and probably the reason why a lot of you are here is through the patient-centric sampling interest group is sample miniaturization, which is often referred to as microsampling. And while venipuncture is typically considered the gold standard for blood collection, it requires, as I mentioned, trained personnel to collect the blood sample, and sample volumes can extend anywhere up to 10 ml for a single blood collection tube, which can then be spun down to collect serum or plasma, depending on that particular tube, before storing at -80 degrees Celsius. In contrast, this process is much more simplified using microsampling. It's much like the way a diabetic would perform a spot glucose test by pricking their finger, simply by lancing the fingertip with a single-use lancet. And this is therefore able to be performed by individuals without professional training. Volumes are generally a lot less. If we look at something like the HemaPen, which is released by Trajan, a commercial device, the volumes are as small as 2.74 microliters, with some other microsampling devices extending collections up to ranges into the 600 microliter range as well in the literature. Like standard venipuncture, some of these microsamples can even be spun down to obtain plasma or serum, or for DBS formats can be stored in dried format as well. So there's that variety in the matrix that can be collected as well. In whole, what we can see here is that this highlights some of the benefits of microsampling with a lot less blood required, with only a few drops compared to a 10 ml tube, It's therefore less invasive, as we're using a small finger prick compared to a needle. Because of this, we can perform sampling more frequently, unlike standard venipuncture, and enhance the richness of our data as part of research. Additionally, it's a lot easier to collect, which means that individuals can perform the collection themselves, and this opens opportunities for decentralized collection and remote sample collection in home settings for patients that aren't able to make it to central clinical settings, and avoids the need sometimes for cold chain shipment protocols as well when we use dried formats. So moving on to the next slide. However, this isn't to say that microsamples are without problems. Traditionally, droplets are collected directly onto filter paper. For instance, a variety of collection substrates like the Whatman 903 protein saver cards, Perkin-Elmer's, and our Alstrom cards are used for direct collection of blood droplets onto the filter paper. And this can result in volumetric inaccuracies, as dispersion of the same volume of blood can be affected depending on a variety of factors. Recently, commercial advanced microsampling devices have been used to overcome this issue. I'll just flash up on the screen here. If you're interested in having a look later on, I'll have it also linked as a QR code at the end. We released a literature review back in 2022 based on some of these microsampling devices that have been employed in the field of metabolic phenotyping, specifically looking at mass spectrometry analysis. And beyond that as well, I also understand that through the patient-centric sampling group, Neil also has a website linked on his page which is updated much more frequently. And I definitely encourage you to have a look on there as well for the different devices that have been utilized as well and on market. To give a very, I suppose, small review, this is by no means comprehensive, but just to illustrate for the purposes of this webinar, these are some of the advanced microsampling devices that are available. And importantly, these devices represent a variety of formats, being that they have dried collections and liquid collections for blood collection volumes, which can extend, like I mentioned, all the way as small as 2.74 microliters, all the way up to 600 microliters in volume. And these allow for these patient-centric collections due to their minimally invasive nature, either by using a lancet or microneedles, and they also don't require trained personnel for that reason. These improve upon that standard blotting technique onto paper substrate cards, like I mentioned. And recently they have undergone application in a variety of research areas. So these include therapeutic drug monitoring, analytical chemistry, drug and alcohol testing, inborn areas of metabolism, and preclinical studies. However, the focus of my research was looking at expanding their scope of these devices in the field of metabolic phenotyping. And this represents an area of research which is focused on the comprehensive biochemical and statistical analysis of small molecules or metabolites within biological samples. These metabolites can provide a dynamic readout of an individual's physiological state and can reflect both genetic influences and environmental exposures. The reason for this is that metabolites are the closest molecules to the phenotype due to their being more downstream of other biomolecules represented in the omics cascade I've included here. And in this way, metabolomics can generate a snapshot of metabolites that are reflective of the immediate changes occurring in the body, for instance, in health or disease states, by using analytical platforms like NMR, or nuclear magnetic resonance spectroscopy, and mass spectrometry, MS. In doing so, they encompass information from other biomolecules upstream of the metabolites and the environmental and external factors that alter them as well. So, despite these sensitive analytical platforms existing for low volumes, the field of metabolic phenotyping still relies on large volume collections like phlebotomy, when we really only need a small sample volume like those that can be collected with a microsampling device or a DBS card, for instance. To put that into perspective with numbers, a typical sample prep for a sample of 10 microliters for a metabolic phenotyping methodology might require something as only as small as 10 microliters. And that could in fact come from a sample that's 10,000 times more in volume at size if it was to come from a 10 ml blood collection tube, highlighting how much volume is not needed as part of this exercise. And then beyond that as well, microsampling not only reduces the sample burden on participants and minimizes sample volumes in general, but it also simplifies analytical workflows in the lab as well. As you can see here, with having the direct mailing to participants, there's no need for central scheduling of clinical appointments, no need for cold chain shipment, and it streamlines the analytical process a lot easier as well. So, to summarize my research interest, microsampling has been underutilized in my area of research of metabolic phenotyping, and most work is centered on traditional DBS, which brings volumetric inaccuracies and problems that I highlighted before. So the gap and what I'm going to be looking at today is quite threefold. My research was to focus on whether we can show equivalence of microsamples to traditional phlebotomy. 2, how we can then optimize extraction and stability of samples for analysis. And then 3, to push that to a more clinical application, particularly for lipid and lipoprotein measurement in real-world cohorts. So I'll start with the first kind of study and aim that I looked at, which was to investigate the equivalence between traditional venous samples and capillary blood. I was really fortunate that this research that I'll be discussing in this section has been published in Analytical Chemistry last year. And this study specifically provided a rigorous comparison between capillary and venous blood and demonstrated how microsampling can be both reliable and practical for real-world applications. A little bit of a shameless self-promo as well. Something that was really cool about being a PhD student was that it was able to be featured on local Channel 9 news, which was something I was really proud of. With my supervisors there, you can see Nicola at the top and Dr. Nathan Lawler at the bottom in the middle, and also one of our lab heads as well, Professor Jeremy Nicholson, which was a really big achievement, something that I was quite proud of. But I'll get into the research side now and discuss some of that. So this study specifically aimed to provide a more accurate and comprehensive understanding of the collection site differences between fingerstick collections and traditional venous collections. And we therefore sought to determine if capillary blood was a suitable alternative to traditional venous phlebotomy for analysis of lipoproteins, supramolecular phospholipid composites, and alpha-1 acid glycoproteins. As measurement of these parameters, using capillary blood microsamples supports a paradigm shift in medicine that moves towards medicine that's more participatory for patients, more preventative, personalized, and predictive. And in the literature, this is known as P4 medicine. So for some context, proton NMR has long been used for rapid measurement of various biochemical signatures in blood plasma and serum in order to understand health and disease states. And these includes measurements of these biomolecules that I mentioned before, lipoproteins, SPIC, which I'll use to mean supramolecular phospholipid composite, and GLIC, which I'll use to reference alpha-1 acid glycoproteins. With advancements in high-resolution methodologies, we now also have diagnostic advantages of being able to perform lipoprotein subclass quantitation, which extends beyond traditional lipoprotein measurements that are routinely measured as part of clinical assessments like your LDL cholesterol and your HDL cholesterol and total triglycerides. Lipoproteins themselves are water-insoluble assemblies that transport lipids in blood, and therefore they're implicated in a variety of diseases that are hallmarked by lipid and lipoprotein dysregulation, such as cardiovascular disease. SPIC and GLIC themselves are additional inflammatory markers, which have been implicated, for instance, in SARS coronavirus 2 infection. And specifically, what have been found is that decreases in SPIC and increases in GLIC have been witnessed in acute inflammation, and therefore their ratio has been proposed as a marker of inflammation themselves. There's some issues, however, in the translation of microsamples for the analysis of these, as largely traditional NMR experiments in 5mm tubes require large sample volumes, up to 500 microliters of plasma, which itself isn't really congruent with microsample volumes. And also the translation to microsampling requires establishing that an equivalence even exists between capillary blood and venous blood for this purpose. So in order to investigate this, my study design was set up like this. I performed matched collection of plasma, so the green top tubes, and serum, the red top tubes, between two collection sites, namely a fingerstick sample for capillary blood and a venipuncture for venous blood. And these matched samples were collected in a cohort of 20 participants. The samples were then analysed via high-field NMR workflow using a Bruker Advanced 3 600 MHz NMR for analysis of 120 parameters of lipoproteins, spics, and glics in total. I won't spend too long on this slide. This is simply just to highlight that everything that was done for the sample prep in the venous blood was performed exactly identical to the sample that was collected from the capillary collection site. And this is also to highlight that the benefit of miniaturizing the workflow down from a 5mm NMR tube down to a 3mm NMR tube, which only required 100 microliters of plasma, was more amenable to capillary finger prick sampling. So if we move on to the next one, in terms of the methodology, these all used Bruker's in vitro diagnostics report methods for lipoprotein analysis, specifically BR-LISA, which is lipoprotein subclass analysis, an IVDR method, and the PhenoRisk PAX method, which derives the spic and glic measurements here. I'm happy to have a chat further about these later on as well, but this is just to highlight the methods, and I've linked them below here as well. In part B of my study design, I also wanted to follow on from the comparison of capillary and venous blood in order to just assess the standard error that was typically associated with a miniaturized sample volume in a 3mm tube. So in order to assess the standard error associated with that measurement, I collected a larger volume of venous blood for analysis over 3 days. So repeat analysis of that blood to see what the standard error associated with the 3mm measurement was itself beyond the collection site. And all the data was summarized into this nice big figure here, which I'll go through and explain step by step, essentially. So to compile all this information for the 120 parameters, we created 2 axes. So on the bottom, we have our adjusted R² axis, and this is represented by the green circles for plasma and the red circles for serum. On the top, we have the axis for standard error, which is in reference to the black dots on each figure. And for the purposes of determining the equivalence between the capillary and venous collection sites, we set a rule to define that the parameters that had a strong significant relationship was an adjusted R² of greater than 0.8 and a significance of less than 0.001. So these parameters that do meet that strong significant relationship criterion are colored in either green or red, with an additional rule for plasma being with that standard error measurement over 3 days. If the plasma circles were shaded, if the capillary and venous error was less than the day-to-day variation associated with the tube. And what we saw was that 86% of parameters, which was 103 out of 120 parameters in plasma, demonstrated this strong significant relationship, which was really nice. And in serum, we saw that there was 88% of parameters, so 106 out of these 120 parameters demonstrated this strong significant relationship across the main parameter families, including the lipoprotein subfractions, spics, and glics. The next step that we then had a look at was if we break this down into the particular markers that are looked at as part of these 120, this included equivalence in clinical lipoprotein fractions that would be normally as part of a pathology visit for lipid markers like your HDL cholesterol and LDL cholesterol. And these markers themselves demonstrated really high equivalence between capillary and venous collection sites with adjusted R² of up to 0.969 for serum LDL cholesterol, which was nice to see. And also some equivalence between atherogenic risk marker, which is the ratio of apolipoprotein B100 to apolipoprotein A1, all the way up to an adjusted R² of 0.968, again, with the significance level across all of these being a P of less than 0.001. Of the parameters that didn't achieve the strong significant relationships, 8 parameters related to HDL and LDL subfractions showed lower standard error in venous plasma technical replicates. And these mainly concern the smaller, more denser subfractions, so the very smallest subfraction of LDL for the particle number, cholesterol marker, and free cholesterol and phospholipid markers. as well as the apolipoprotein B100. Despite this, these measurements still demonstrated moderate explained variance with an adjusted R-squared range from 0.658 to 0.773, suggesting that measurement of these subfractions in capillary microsamples is still a biologically valid alternative to traditional venous phlebotomy for this purpose. And we can also look at this as well using the spectra. So when we overlay the 1D spectra, which derives the lipoprotein parameters, we can see here that there's good overlap and relationship between both venous and capillary plasma and serum, and no differences were seen between the collection sites. However, when we have a little bit of a look at the pulse gradient perfect echo experiment, which derives the spic and glic parameters, what we noticed was that although there's nice overlay between the collection sites in plasma, there is a little bit of a smaller difference, particularly towards the lower frequency SPIC1 witnessed in serum samples. And what we likely postulated this down to was that there was differences in clotting dynamics from the serum sample collection compared to plasma. And there's also implications for the equivalence between venous and capillary blood due to temperature that clotting occurs at, and also potential dilution from the introduction of tissue factor when squeezing, let's say if you're collecting your fingerstick sample. Therefore, some recommendations that were highlighted as part of this research was, if you are going to be looking at the supramolecular phospholipid composites and the GLIC composites, selection of plasma tubes would be better over serum ones, so either heparinized plasma, and also the use of high-flow lancets compared to your traditional lancets. So the high-flow lancets like the BD lancet in blue that I have there allow for collection of blood at a much more nicer flow rate without the need to add additional pressure for collection of a blood sample, and will mitigate that in a patient collection setting as well. So based on these results, we then wanted to advance our findings to see if it was possible to translate analysis down to a low field benchtop NMR, as benchtop spectrometers are a much more cost-effective alternative for measurement of these biomarkers at point of care. And preliminary analysis for this was performed on 2 individuals, again for collection of matched venous and capillary plasma samples, and these samples were analyzed on an 80 megahertz benchtop NMR. We know from previous literature that the low field or 80 megahertz measurement correlates quite nicely with the high field 600 megahertz measurement, as you can see there in that first figure. In the present study, we wanted to extend this, and what we saw was that we witnessed an overlap between capillary and venous collection sites as well when we overlaid the spectra. Ultimately, what this preliminary data suggested is that microsamples were translatable for routine measurement of SPIC and GLIC using field deployable 80 megahertz benchtop approaches without need for trained phlebotomists. So overall, in conclusion, this study focused on if microsamples were a suitable alternative to venous ones for measurement of these lipoprotein, SPIC and GLIC parameters. And what we found was that there is a good correlation between the two. However, some recommendations, particularly for SPIC measurements, was selection of plasma tubes and use of high-flow lancets to allow for the best equivalence between the 2 collection sites. We then investigated a field deployable application, which highlighted that for the SPIC and GLIC measurements, this could be an alternative for routine and point-of-care assessment in community settings. Cool. So to direct focus now to the second aim in translating this further down to a smaller method using a dried blood spot card, building on that the lipoprotein work, we wanted to then look at miniaturizing that further. And the research I'll be discussing in this section was published in Atlanta and represents a semi-quantitative 4D lipidomics approach for dried blood spots using a high-resolution mass spectrometry approach. Our goal here was to develop a workflow that leverages the advantages of DBS, including the minimal sample volume, patient-centric sampling, and simplified storage and transport. And the workflow enhances the integration of microsampling into metabolic phenotyping studies to reduce the reliance on traditional phlebotomy, making population level research, remote sampling, and personalized medicine more feasible. photo here of the article that's associated with it if you're interested, which you can access the QR code at the end. Cool. So the research question, I suppose that was the main focus of this work, was whether or not advanced DBS microsamples were suitable for untargeted lipidomic profiling. To provide a bit more context to this, I used a trapped ion mobility spectrometry, or TIMS approach, which enables accurate measurement of metabolite collisional cross-section, or CCS. These CCS values are a core component of 4D metabolic profiling workflows and provide confidence in compound annotation that can also augment accurate mass, isotopic pattern fit, retention time, and MS data that is routinely generated in high-resolution mass spectrometry workflows. As part of my study design, I've just laid this out here so you can see how I went about conducting this research to develop this method for mass spectrometry. We wanted to essentially assess a variety of parameters that were applicable to DBS microsamples to ensure a practical workflow for lipid analysis from a DBS. This included sample preparation, extraction, substrate selection, and stability, as well as then validating this in a real-world cohort in order to ensure that patients could self-collect these samples and they could be analysed sufficiently. So to begin, I compared two common DBS preparation methods that you might be familiar with from the literature, namely a 3 mm sub-punch from the centre of the disc versus a whole disc extraction technique. And I compared these two extraction techniques on a pre-validated targeted method that we had in-house for 9 different monophasic extraction solvents that I found across the literature for lipidomics. The method comprised 1,163 lipids across 20 lipid subclasses and performed semi-quantitation using 67 internal standards. What we identified from these data is that in replicate DBS samples, whole spots had a greater recovery of lipids with less than 30% RSD. And so we selected the top 3 extraction solvents, which were namely 80% IPA in water, IPA, and ACN, to continue on for further testing as part of the development of the untargeted method as well. When comparing the top 3 extraction solvents on the untargeted platform, what we found was that 80% IPA was identified as the leader and had the greatest number of unique and rule-based annotated lipids. Specifically, we identified 373 unique lipids in positive heated electrospray ionization mode and 282 unique lipids in negative heated electrospray ionization mode. Next, we then looked at the DBS substrate and the performance essentially of the whole disc extraction with that 80% IPA across common DBS substrates that are used in the literature. Namely, this included the Whatman 903 card, the Perkin-Elmer 226, and the Austrom 222 cards, which are commonly utilized in a variety of advanced microsampling devices. And these all performed quite similarly, each with good repeatability within substrate. And I've just included the PCAs and Venn diagrams here for the different acquisition modes in positive and negative ionization modes. For storage, one note here on DBS substrates in negative mode, we did notice that there was a greater intensity for lipids that were recoverable across all 3 substrates, particularly leaning towards more thinner DBS cards. For instance, the Whatman 903 showed a greater intensity, and this was hypothesized due to improved solvent absorption on the card, being a thinner DBS substrate. We then wanted to have a look at storage stability, and to do this, we took the stability of the 2 of the most common cards used in advanced microsampling devices, investigating them under real-world conditions to see their performance up to 3 months of storage time in order to investigate their performance for lipidomics. What we did was perform a calculation of the fold change of triplicate medians, and anything that was greater than 30% of the control is anything essentially outside of the grey box range here from 4 hours all the way up to 3 months, wherever that bar is outside the dark grey box. What we identified is that there's feasibility for remote collection at conventional fridge and freezer temperatures, namely -20 degrees and 4 degrees Celsius at up to 2 weeks. But unsurprisingly, there was decreasing stability with increased temperature, particularly in lipid classes like our lysoglycerophospholipids and our glycerophospholipid classes, where an inverse relationship was noted. So we have an increase in lysoglycerophospholipids and a decrease in glycerophospholipids. And we've hypothesized this is likely due to the increased activation of phospholipase A2 enzyme at higher temperatures, which is understood from the literature. In terms of self-collection, now that we had some promising stability data, we then wanted to see if this could successfully be translated to participant self-collection. And we performed a mini trial on 6 participants using 3 time points across 1 hour. And to do that, we used the Capillary card, which embeds the Alstrom substrate. Based on the data from this trial, what we noticed was that there was minimal influence on the lipidome over an hour, and that inter-individual differences exerted a greater effect, which is seen really nicely in the participant stratification across principal components 1 to 3 in the figure that I've included up here on the slide. And I won't spend too long on this one here, as it's a bit more technical, but we also investigated a single point semi-quantitative technique using the Equivalence Lipidomics internal standard from Avanti Polar Lipids. And unsurprisingly, the reproducibility within triplicates improved using internal standards across all 432 unique lipids from the method, all of them having a CV of less than 25%, compared to the raw peak area, which you can see here across both positive and negative modes. There's some lipids that still sit above that when using the raw peak area compared to with the semi-quantitation with the internal standard. And one more note on that, the extracted ion chromatograms, just to show each of these standards being able to be recovered in the acquisition. Please note that we didn't see cholesterol esters, triacylglycerols, or monoacylglycerol internal standards in negative mode, as we'd expect. So the conclusions from this second part of the study was that we aim to develop a high-resolution method to analyze lipids in DBS samples to continue that miniaturization workflow. We evaluated 3 extraction solvents and compared a variety of parameters that are important to practically setting up a method to ensure that it can be deployed in real-world settings, including appropriate extraction technique, comparison of different substrates and their performance, and evaluation of stability, and optimize these parameters to ensure that they could be performed in a self-collection study. The last aim then, and the last part of this webinar, will be focusing on now the application that we have a robust method in place. We now wanted to shift our focus to a specific clinical application, in this case, diabetes. In this study, we apply that DBS microsampling workflow to profile the diabetic lipidome. So to begin with, just as a little bit of a background on the biology of diabetes, it's a chronic cardiometabolic disorder. It affects over 830 million individuals worldwide and is characterized by acquired insulin resistance, which leads to disrupted glycemic control and dysregulated lipid metabolism. And this underpins its strong association with cardiovascular comorbidities and contributes to increased global mortality. A metabolic hallmark in diabetes is dyslipidemia, where we see imbalances in lipid homeostasis, which results in abnormal blood lipid profiles. And these alterations can accelerate progression of cardiovascular diseases such as atherosclerosis, thrombosis, myocardial infarctions, alongside other complications like neuropathy and retinopathy. Current diagnostic monitoring strategies rely heavily on glycated hemoglobin, or HbA1c, which provides a marker of glycemic control over the prior 2 to 3 months. And while HbA1c is effective for assessing dysglycemia, it offers limited insight into lipid metabolism, restricting the scope of information available to guide metabolic management. Moreover, these assessments typically rely on venous phlebotomy, which is an invasive procedure, as we know, and this can cause discomfort and deter routine monitoring. Additionally, phlebotomy requires trained personnel, specialized equipment, and cold chain transport to preserve sample integrity, which can contribute to an increased cost and reduce feasibility in rural and resource-limited settings. And given the disproportionate burden of diabetes in such communities, these challenges really highlight the urgent need for more accessible and scalable sampling methods to support long-term disease monitoring. So this highlights diabetes, in this case, as a really appropriate choice for where microsampling can be routinely employed. Given its role in disease progression, dyslipidemia makes diabetes a relevant context for detailed lipidomic investigation. And recently, DBS microsampling technologies have been explored for comprehensive lipid profiling. Low-volume samples such as DBS are well suited for high-resolution mass spec, as we saw from the previous research and method development, as they offer sensitivity and improved resolution. For instance, with methods like trap time mobility spectrometry, mass spectrometry, allowing for lipid collisional cross-section measurement as an additional dimension to complement accurate mass, isotope patterns, and MSMS spectra to improve that annotation of lipids. In this way, using microsamples with HRMS can improve our understanding of lipid dysregulation in chronic diseases like diabetes in a more patient-centric manner. So the research question essentially for this became, as diabetes is a growing health challenge that's closely linked to dysregulated lipid metabolism, and whilst the precise mechanisms underlying insulin resistance and diabetes are not fully understood, the literature suggests that dyslipidemia is a key contributor to disease progression, which is why we focused on applying our lipidomic method in a diabetic cohort. As an added bonus, diabetics are more accustomed to performing finger pricks to perform spot glucose testing. And so we were interested in also capturing some qualitative feedback by way of surveys on their perceptions to microsampling too, which I'm happy to go through at the end, and use some really promising data which we were able to collect. So to investigate the feasibility of DBS for assessing lipid dysregulation in diabetes, we recruited 34 participants, 17 non-diabetics and 17 diabetics from the Perth metropolitan area here in Western Australia, with each group made up of 8 males and 9 females. Of note, in the diabetic group, 15 of 17 were diagnosed as type 2 diabetic, so it is more predominantly type 2 diabetic population. And on average, the non-diabetic controls had lower weight, BMI, and fasting glucose levels. For the sample collection, participants attended a clinic for collection of 3 sample types, namely a DBS microsample and capillary plasma, which was self-collected by the participants, as well as venous plasma sample, which was collected by a trained phlebotomist. As an additional aim, we also wanted to capture how acceptable microsampling might be in this population. And since individuals with diabetes are already familiar with finger prick testing for spot glucose blood assessment, we included a short pre-validated survey in order to explore their perceptions and experiences with microsampling in a research setting. And for analysis of the samples, as I introduced before, we used pre-validated and published semi-quantitative 4D lipidomic profile, which I went through before, and I won't spend any further discussing that one there. So in order to perform statistical analysis, we used OPLSDA to analyze between group differences using R, specifically using the MVA plots package. And I also examined lipid side chains in a similar approach to Lipidome R, looking at 2 levels, specifically the fatty ASR level and the summed species lipid level, in order to stratify participants to see if there were differences in the lipid profile. So getting into some of the data, quite nicely, all biofluids yielded statistically robust OPLSDA models for diabetes discrimination. And interestingly, DBS showed comparable and sometimes even slightly superior performance to venous plasma in terms of the R²Y and prediction error, highlighting its promise for patient-centric lipidomics, which is really cool to see. Move to the next one. And then when examining the top 12 lipids that were driving this difference for each group based on VIP score and colored based on the Cohen's D, there was consistency in the top lipids that were driving this separation, which was nice to see across all the biofluids as well. Specifically, glycerolipids including trace or glycerols in the diabetic group, and glycerophospholipids such as lysophosphatidyl-choline, phosphocholine, and sphingolipids such as hexosylceramides were consistent across venous plasma, capillary plasma, and the DBS sample in driving those differences. When we had a look at their concentrations from the semi-quantitative workflow, these are shown here by sample type. As expected, our DBS samples show a lower concentration, which is to be expected given that it is a whole blood sample rather than a plasma sample. But importantly, they still reveal significant differences between the control and the diabetic group, showing the ability to retain biologically relevant lipids for stratifying diabetic and control phenotypes. After establishing that the ability of the DBS to capture this information and being comparable with traditional plasma measurements, we then wanted to look at how structural composition of the individual lipids can distinguish diabetic participants from non-diabetic ones in the DBS sample. And this plot here visualizes the VIP scores of individual lipid side chains across different lipid subclasses at the fatty acyl level, which allows us to see which fatty acyl chain compositions are most influential in distinguishing diabetic and non-diabetic phenotypes. What I've plotted here essentially are lipid subclasses on the x-axis against the side chain composition on the y-axis, with the size indicating the VIP score, where red's representing a stronger association with diabetes and blue representing a stronger association with the controls based on the Cohen's D. Most notably, what we see is for glycerolipids such as diacylglycerols and triacylglycerol species, they show a more notable enrichment in diabetes, particularly for longer chain and more unsaturated species, for instance, R22,6 and R24 side chains. Also notably, what we see as well is that LPC species uniformly have higher VIP scores in our controls, the blue represented there on the figure. And shorter, more saturated / unsaturated side chains tend to have stronger associations with controls across multiple lipid subclasses. Continuing this, I then summed the side chains of lipid species in order to examine how the total degree of unsaturation and summed acyl chain carbon content appears across the different lipid subclasses. And again, quite nicely, what we can see here is that the LPCs ubiquitously are higher in our controls for all acyl chain lengths and degrees of unsaturation. Importantly, this is consistent with diabetes pathology and previous plasma lipidomics research, which has also similarly seen net LPC reductions in type 2 diabetes. And also the presence of, more polyunsaturated triacylglycerols in the diabetic group is shown with an increasing trend in VIP score. As you can see, greater total carbon content and greater degree of unsaturation having larger circles. Additionally, lipids with higher total acyl carbons, typically composed of saturated or monounsaturated acyl side chains, appear higher in diabetics, the red ones, for example, the ceramides, ether-linked PC species, and sphingomyelins, while lipids with lower total acyl carbons, typically composed of polyunsaturated acyl chains, appear more associated with non-diabetic controls represented in blue, for example, the ether-linked phosphotidylcholine species and sphingomyelins, which may suggest that combined acyl carbons and degree of unsaturation may be key features in distinguishing diabetics from control lipidomic profiles. Lastly, as part of this slide, and something that was really cool to see as part of this research, was that we employed a survey on perceptions to microsampling specific for self-sampling with the Capillary device using a pre-validated survey that employs Likert scales to assess clarity of instructions, ease of collection, and preference over traditional phlebotomy. Questions 7 to 8 here require selection from discrete options rather than a Likert scale, and uncontroversially, non-diabetic controls reported never performing finger pricks on average, and a small significant difference was also noted for highest level of education achieved between the two groups. Question 9 uses another Likert scale in order to assess pain from the Lancet from 1 to 10. And here what we saw was that diabetics reported less pain on average out of 10 compared to non-diabetic controls. However, self-sampling was well received overall and no one reported a pain score above 3, which was really cool to see for the finger prick sampling. So the key takeaways from this final research was that self-collected DBS are a viable alternative to venous blood for diabetes lipid research. There's robust lipidomic distinctions observed in different lipid subclasses, and participants really happily endorse the DBS sampling for its convenience and ease of use. So the future from here and looking ahead is at validating the findings across larger, more diverse cohorts, emphasizing access and equity, especially in remote and underserved populations, and potential to expand to more longitudinal collections, particularly with the ability to perform more frequent sampling using microsamples. And as part of this, what I suppose on a personal level I'm doing is actively seeking collaboration and partners through the Australian patient-centric sampling interest group, which is a task group that Neil has helped set up for my region to help co-develop best practices, use cases, and drive adoption of microsampling as well. And overall, I'd like to thank everyone for listening. I'd also like to acknowledge all the participants that were involved in all of these research studies, my supervisors at the Australian National Phenome Centre and Centre for Computational Systems Medicine, Brooker, and especially Patient-Centric Sampling Interest Group for having me here today and presenting my research to you all. Thank you. I've popped my QR code there. If you're interested, you'd like to connect or read any of my research, I'm more than happy for you to reach out. I'd love to discuss. Thanks.
Thank you, Jayden. Really interesting. Lots of fascinating data there. I'm sure your thesis defense went really, really well, and congratulations on getting all those publications and getting your PhD on this wonderful work. So let's see if we've got a few questions from people. Please submit your questions through the chat function on this browser. We have a question from Peter. He says, how important is time of day or time after a meal or exercise? Perhaps less with lipids than for more hydrophilic small molecules.
That's a really good question. In terms of exercise, I haven't personally investigated that one. I know my supervisor, who does a lot of biomechanics research, would be really great to answer something like that, but I'm happy to put you in contact. In terms of food, though, this one is something that we have seen quite significantly in some of our samples that we've collected, just in terms of during our method development stage, where if someone has had a very fatty meal, for instance, something like milk especially can rapidly change the lipid content around an hour or so after, and there are noticeable differences in the lipid profile, even in the microsamples.
So a question from me, Jayden, how do you see this moving forward into general healthcare?
In terms of general healthcare, I think something that's really important and at the forefront here with the microsampling research is being able to put this into point of care settings, particularly with methods kind of like what we were able to showcase here with the lipoprotein measurement and the inflammatory marker measurement. Having that point of care testing available using a benchtop instrument, maybe somewhere like a pharmacy or a GP clinic, might be able to help with more routine diagnostics in more routine care settings outside of central clinical settings.
And do you think the NMR or the mass spec approach would fit better into those situations? Or, I mean, I'm guessing we need a next generation of instrumentation regardless in order to put it into a pharmacist. I'm getting,
absolutely. Mass spec might be a bit trickier, but
yeah.
I think definitely with the benchtop NMR, given the very minimal sample preparation that's involved, its non-destructive nature, and benchtop instrumentation, it's definitely something that could be employed more readily in a point of care setting.
And obviously the software to crunch all the numbers on there, all the different parameters simultaneously, and just having a data presentation becomes the big thing, doesn't it? Simplifying all that data into something that's understandable by the patient, by the clinician, the pharmacist.
Yeah, absolutely.
Is that something you'll be working on in your future research, Jayden? Are you going to be staying in this area?
Yeah, in terms of that specific side. I know with the benchtop instrumentation, a lot of the research now at the lab where I did this research is looking at integrating with the hospital on our campus. And they've actually set up a benchtop spectrometer for that purpose in order to continue this research and deploy it in a way that can showcase its ability in these settings.
Oh, that's cool. And the feedback from clinicians and patients there is going to be so important.
Oh yeah, it's going to be so interesting, especially now that there's also they've also been able to translate this down to the lipoprotein subfractions as well, beyond just spic and glic. So a lot more parameters that can be looked at with a benchtop instrument, which is really cool.
Oh, very interesting. Just a comment from Jeremiah. Thank you for the excellent presentation. Thank you, Jeremiah.
Thanks,
Martina says, did you test different chromatographic columns for lipid separation?
We didn't, unfortunately, Martina. Our lipid method was developed on an in-house method that already existed for a targeted workflow. So as part of that targeted method development, there was a difference in columns that were trialed between C18 and a BEH amide and one other that's evading me at the moment. But what was found as part of that targeted method development was that the C18 performed superior for the particular analysis. And so we continued with that C18 column as well.
Cool. As you're in Australia, long way from us, and here in Europe and our normal attendees in North America, just thought whether you got any comments on the applicability of these patient-centric sampling and this kind of multi-omics approach in Australia. Do you think it's going to be a good fit in your health systems at all?
Definitely. I think given the geographic spread in Australia, even just alone in Western Australia, where I'm from, being able to connect to a lot more locations that don't have as much access to healthcare infrastructure through microsampling will be a big game changer in the area. And being able to allow patients to be at the forefront of it and collect their own samples and ship them into central care settings is going to be a big, is going to be the next thing.
Yeah, that's cool. So it looks like we're not getting any other questions in. I'm just going to ask you one more myself, give people a little bit of time to get in their last minute questions. For our snippets that we'll produce after this event, do you have one quick takeaway message that you'd like to give?
One takeaway message?
Yeah.
Oh, it's hard. How do you condense a thesis into one takeaway message? I think I'm just so excited to see where microsampling will head in the next few years. At the beginning of my PhD in metabolic phenotyping, applications were relatively smaller in 2021, 2022, and it's just exponentially growing now. So I'm really excited to see where it's going to lead and the amazing developments that are going to come from it for patients.
Yeah, I agree. I think we're reaching a tipping point. I think it's exciting, and the future's bright for your kind of research and helping patients hopefully in the future. So I'm just going to move on to a couple of slides from the patient-centric sampling interest group. Sarah says, excellent work, Jayden, by the way.
Thanks, Sarah.
Thank you, Sarah. So just for those that don't know about the patient-centric sampling interest group, we're a not-for-profit group, global membership. If you want to learn more about us, please use the QR code to visit our website. You're welcome to join our LinkedIn group. Use the QR code on the right. We're always welcoming new members with new insights and helping us to form new working groups to just help move the frontiers and educate people on what patient-centric sampling is, what the implications are, what the challenges are, and how we overcome those. So please, if you're interested, get involved. Just for our upcoming webinars, we've got Giovanna talking to us about urine sampling and alternative ways of patient-centric ways of urine sampling. And she's talking about is unreliable point-of-care urine collection putting women on the front line of antimicrobial resistance. So Giovanna's always a very entertaining speaker, so I recommend that one. And we've also got Rachel Carling coming in April, talking about evidence versus adoption in PKU monitoring, understanding the implementation gap. So two great webinars coming. We've actually got webinars booked now out to March 2027, but if anyone's got any suggestions for additional webinars, please write to me at neil@pcsig.org, and be happy to have a conversation about a potential webinar. Finally, just like to thank all of our partners and sponsors again, without whom we couldn't have these events. And finally, just big thank you to Jayden, and thank you to you, the audience, for attending today. It's been really interesting, and this recording will be live in about a week's time. And no further ado, wish you all good day.